The vertex cover problem is a decision problem where the input is an undirected graph G and an integer k. And the question is, does G have a vertex cover of size at most k? To understand this problem, we need to know what a vertex cover is. A vertex cover is a set of vertices in the graph, such that every edge in the graph is incident to at least one of the vertices, meaning that at least one of the endpoints of every edge belongs to this set of vertices. Consider the following graph as an example. Let k be equal to 5. There does indeed exist a vertex cover of size 5. Every edge in this graph is incident to at least one of the vertices, 3, 2, 6, 4, and 7. The vertex cover problem is clearly an NP because if given a set of vertices, we can check if it is a vertex cover of size at most k in polynomial time. Hence, we can show that it is an NP-complete problem by showing it is NP-hard. This can be done by reducing the 3-SAT problem, which we know is NP-complete, to the vertex cover problem. Given an arbitrary instance of the 3-SAT problem, we need to construct an instance of the vertex cover problem such that the answer to the 3-SAT instance is yes, if and only if the answer to the constructed instance of the vertex cover problem is yes. Recall that an instance of the 3-SAT problem consists of n variables and m clauses, where there are exactly 3 literals in each clause. A literal is a variable or its negation, and a clause is a disjunction of literals. The input is always a conjunction of the clauses. For each variable, we construct a node for that variable and join it with another node representing its negation. Next, we create a triangle for each clause, where the nodes represent the literals in the clause. Then, we connect each literal in the clause to its corresponding node in the graphs we created for each variable. We can cover the edge in each variable pair by selecting exactly one vertex. Selecting any 2 vertices from each clause triangle ensures the triangle's edges are covered. Therefore, let k be the number of variables plus twice the number of clauses. Suppose that the 3-SAT instance is satisfiable. For each variable, add the variable in the variable pair if it is set to true, and add its negation if it is set to false. Since the 3-SAT instance is satisfiable, at least one literal in each clause is true. This implies that at least one of the 3 edges that connect a clause triangle to the variable pairs is already covered. Thus, we simply choose the other 2 vertices in the clause triangle to cover the other 2 edges. This shows that there exists a vertex cover of size k. For the other direction, suppose that there exists a vertex cover of size at most k. We need a minimum of 1 node in each variable pair to cover its edge, and a minimum of 2 nodes in each clause triangle to cover the triangle's edges. Therefore, the size of the vertex cover must be exactly k, where it has exactly 1 vertex from each variable pair, and exactly 2 vertices from each clause triangle. Since all the edges that connect the clause triangles to the variable pairs are covered, there must be at least 1 literal in each clause that is true. Otherwise, we would need to include all 3 vertices in the clause triangle to cover the edges. This completes the proof, and we conclude that the vertex cover problem is an NP-complete problem.